Now let's get to memory allocation. How can we allocate memory? So the first thing we're going to talk about is contiguous allocation. So under this paradigm, the resident operating system is actually, so we divide the main memory into two sections. The first is the resident OS, which is usually held in high memory, and then all the other user processes are held in low memory. So each process will be contained in a single contiguous section of memory, next to it the other process, and so on. So when the CPU scheduler selects a process to be executed, then the dispatcher, right, remember the dispatcher module that takes care of context switching. So the dispatcher will load the limit registers as well as the relocation register, which we called base register earlier, and then check that it falls within the correct range and it has the correct values as part of context switching. So this operation is done as part of context switch that the dispatcher does. So under contiguous memory allocation, variable size partitions are used where the partition is actually sized to a given process's need, okay? And so we will end up with the operating system in the high memory and then the processes in their allocated sized partitions, okay? So these partitions will not have the same size for different processes. Each process will have its own different size. And then we talk about the holes. We define holes as these empty partitions in memory that are not yet allocated, and they're scattered throughout memory. So we define the dynamic storage allocation problem as the problem of how to satisfy a request of size n from a process from a list of free holes that we have in the memory. So how can we find the right space, the right partition for a process of size n? So that's what we're trying to solve, the dynamic storage allocation problem. So there is mainly three ways. There may be more, but we're just going to discuss three main ones to solve the dynamic storage allocation problem. So the first is called first fit. So out of a list of allocated and free partitions in memory, we're gonna start searching our memory, and then we're gonna allocate the first partition found that a process of size n can fit in. Okay, that's first fit. So the search stops as soon as we find a partition that can hold the process of size n. Now with best fit, we're going to search the entire memory for the smallest hole that we can find where process P can still fit in. So if we have 10 holes and all of them, let's say if we have 3 holes, so one has a size of 4, one has a size of 10, and one has a size of 100. Our process is of size, let's say 9. Then the best fit algorithm will look through the entire list of free holes. It's going to find 4, 10, and 100, and it's going to pick the smallest one where process n can still fit, which is 10. Okay, so that's best fit. Now the worst fit is the opposite. It will find the largest hole where process P can fit, which is in this case 100. Okay, so First fit is efficient, but it doesn't make a good use of memory. Whereas best and worst fit, they do involve searching the entire list of freeholds to find one. The other difference is if we're using the best fit and we're picking the smallest hole, this will result with the smallest leftovers. So leftover is that tiny little hole empty here that is left off after we've allocated the hole to a new process. If we were using worst fit, the leftover hole will be bigger compared to the best fit. And so if we have this list of 4 holes, A to D, and these are their corresponding sizes, if we were using first fit and we want to allocate space for a process of size 10 bytes, then the first one, so we start searching either from left or right, it doesn't matter. So let's say that the algorithm will start from left to right, and then we found the hole A, but it's not big enough. Then we find the hole B, where we see that 10 can fit in B, so we're gonna pick B. Now, if we are using best fit, then we will compare all the 4 holes that we have. The smallest of them is 5, but the process will not fit in. The next smallest is 11, and that's a good choice if we're using best fit. However, if you're using worst fit, of course, we're going to use the biggest hole, which is of size 100 bytes, and that's where we're going to put our process. So variable size partition allocation creates a problem that's called external fragmentation. So external fragmentation is those leftover holes that we talked about earlier. So it's those free spaces that exist in memory, but they are actually scattered all over the place, and they're not combined, and so we cannot really fit a process in them. So we do have empty space, but it's not combined together to form a larger whole where we can put a new process in. So we call this external fragmentation. On the other hand, there is another type of fragmentation that is called internal fragmentation. The idea is you assign this partition to process A, but it ends up not using a part of it. So we call this internal fragmentation. So it's a wasted space, but it's internal to that process. Versus external, it's not yet allocated, but it is small and it's scattered all over the memory that we cannot really put a process that can fit in it. One possible solution to fragmentation is compaction. So the idea with compaction, so we're presented with some here allocated partitions and empty ones. One idea to do compaction is, so compaction means to shuffle the memory contents in order to move the allocated partitions to one side and put and merge the free partitions to the other side. Okay, so that's what we just did right here. So we can move the we can move the allocated spaces either to the left or to the right. It doesn't matter, but the main advantage is that we're putting and merging the free holes together. Another idea is we don't have to move all the allocated spaces to one side, so we can start moving them one by one. So we move this this allocated area right here. We still can't fit this, so this is the new process that we're trying to fit in. So if we move just the first one, we still can't fit a process of size 10. And then if we move 5 again, then we end up having these two partitions here, and we're gonna end up having this free space here where we put our new process in, and we stop. So the algorithm stops here. We do not have to move those any more extra allocated partitions. We only we stop when we do actually have enough empty hole to accommodate and to accept that new coming process. There are more sophisticated algorithms or versions to do compaction. Is if we look at the original view, we can see that if we just move this partition right here, this allocated partition, into this free hole, then we're going to end up with this big empty space where our process of size 10 can fit in. And this is what we did right here. Okay, so we only moved one allocation, but again, this is more complex, more time consuming to actually reason and find the correct partition that has to be moved.